Oh, wow. And now I realize how much I miss actually meeting people in person.
We were lucky that some of the best conferences happened last year, you know.
Yeah.
Yeah, Anastasia, is it okay if I record the talk and put it on YouTube later to earn some money?
Exactly. I mean, aren't you afraid of going viral with it?
No, I am. Yeah.
Yeah, of course.
But how many followers do we have actually?
I think 38 now.
38. Oh, no bad.
We're getting there. We're getting there. It's going exponentially.
So I think we can start. Before passing to Nastya, I would like to introduce her in few words. Anastasia Borschevsky, she got her PhD degree in 2010 from the Tel Aviv University under the supervision of Professor Otzi Kaldor and Professor Ephraim Ilyav. Her first postdoc experience, she did it in Massey University in New Zealand, collaborating and working together with Peter Schwertfeger. And then she came to Europe to the Superheavy Element Group, GSI, and Helmholtz Institute in Mainz, and worked there for a while until 2015, right? And then she received in 2015 the Rosalind Franklin Fellowship at the University of Groningen and got a tenure track position there. And she received a number of grants, for instance, the VD Personal Grant with a lot of money. And also she is a member of Lisa Etienne Network. And this year she received the tenure and got promoted as an associate professor in Groningen. This is, we can congratulate you for this achievement. Very nice. Yeah, today we are happy to have you here speaking to us about atoms and molecules as probes for physics beyond the standard model. Nastya, please.
All right, I'll share my screen. You should see my slides. Are they full screen? I think not.
Not yet.
Not yet. Full screen mode, yes.
Yes, now?
Great.
Yeah, and do you see the pointer?
Yes.
Yes, okay, excellent. Yeah, well, thank you very much for the invitation to present my research here, and thank you, Mustafa, for the nice introduction. As I was saying, I have given talks in Mainz a few times in various workshops and conferences and seminars, but this is the first time that I'm giving a talk in Mainz while not being in Mainz, so okay, that's a new experience. Right, so I'm going to talk about how we can use atoms and molecules as probes of physics beyond the standard model. I'll start by introducing myself for those who have not met me before. Yeah, so I work at the University of Groningen, which is in the very north of the Netherlands. This is our main academy building, and this picture is actually quite misleading because you can see the blue sky in the background. Well, that doesn't really happen. So this is how it normally looks. So this is, yeah, if I turn my screen a bit, you would see the same thing out of my window. I have a good-sized group at the moment. I have 6 PhD students working with me and the postdoc. And in my group, we use computational chemistry methods, very accurate methods from computational chemistry to address fundamental problems in physics. And of course, this sounds very vague and quite grand, but in terms of topics, we work on two main subjects. We work on search for new physical phenomena using low energy precision measurements, like violation of fundamental symmetries in atoms and molecules, or a search for variation of fundamental constants also with atoms and molecules. And there is a somewhat less exotic part of our work where we perform high accuracy calculations of spectra and properties of heavy and super heavy elements, highly charged ions in spectroscopic context. These two topics are related to each other and often kind of entangled together. And what is also nice in our work is that most of the things we do in collaboration with experimental groups, which of course
Möglichkeit, eine Nachricht zu hinterlassen, die Sie anschließend abhören können.
I think someone has the microphone on.
I think Klaus, or isn't it?
Okay, oh, it stopped.
Stopped. Okay.
Right. Yeah, so we work with experimental groups, which on one hand is of course very rewarding. It's very nice to have our research directly related to work that other people are doing. On the other hand, it also makes our life slightly more difficult as it imposes some conditions on how we work. So it means that, for example, we need to figure out a way to put error bars on our predictions, which most theoreticians do not usually do. So that's kind of special in this sense, in particular in comparison to computational chemists. This is quite unusual. All right, and yeah, today I'll focus on one topic. I'll focus on the first topic, so search for new physics with low energy precision measurements. And I was actually going to cover the two subjects, also search for variation of fundamental constants, but unfortunately, when I was preparing my slides a couple of days ago, I realized that as it is, I'm in danger of going over time, so I was limiting myself to one topic. All right, so before I talk about how we do this, I'll spend a bit of time on motivation and ask some why questions. So first question is, why do we want to look for physics beyond the standard model or new physical phenomena? Of course, we know that the standard model is currently the best description of the physical world that we have. It's very successful in describing the observed natural phenomena. It unites the 3 out of 4 fundamental forces and describes all known particles. And it also has very strong predictive power, as we know, for example, saw in the discovery of the Higgs boson, but also top quark and tau neutrinos, which were all predicted theoretically before their discovery. So yeah, so this model is very successful, but unfortunately it's incomplete. And there is a number of issues with the standard model. One is that it doesn't include general relativity, and we do not really know of how to connect gravitation with quantum physics. So this link is not completely clear, how to unite gravitation with the other forces. In addition to that, also some very important questions remain unanswered. And the most disturbing of them are perhaps also most fundamental. So the reason why we have matter-antimatter asymmetry. According to the standard model, we should have equal amounts of matter and antimatter, which would probably have annihilated to create energy, but we see that we have matter around us. So this asymmetry is not clear what the origin is and why it's there. And yeah, standard model doesn't explain that. And another thing which is of concern is the fact that, well, we know about that ordinary matter comprises about 5% of all matter in the universe. We call the rest of it dark matter and dark energy, but we do not actually know what kind of particles are those and what their origin is. And again, the standard model doesn't provide us with answers to this question. So this means that, okay, this model is not complete, and this means that There are many extensions to the standard model being developed by in particle physics. And these extensions attempt to fill these knowledge gaps. There's many different models, many different theories, more or less exotic. And what is common to most of them is, besides trying to complete the standard model, within the process of completing the standard model, they also predict new phenomena, which we have not yet seen. And example of such phenomena are variation of fundamental constants or violation of fundamental symmetries, like parity or time reversal or charge conjugation symmetries. Many orders of magnitude beyond that allowed or predicted in the standard model. And what is nice about these predictions is that this phenomena can serve as sort of fingerprints or signals for these new models. So basically, if we detect this phenomena, this allows us to confirm some theories, or depending on their magnitude, also disprove some of them. And also a non-detection or non-discovery, if one can put a stringent upper limit on whatever phenomena we're talking about, is also useful for differentiating between the models. All right. So this is why, and this means that there's a lot of experimental efforts to detect, to look for these effects. So the next question is, why do we use atoms and molecules for this research? And in fact, we can do different things. We can use accelerator research, high energy research, to look for direct parity violation. This is what done at LHCb in CERN and or T2K experiment. But another very attractive alternative is tabletop or lab-sized experiments, low energy experiments, high precision measurements on atoms and molecules. And such experiments have many advantages, or there's many nice things about them, which make them competitive to accelerate research. So first of all, atoms and molecules are very versatile test systems. They can be sensitive to a wide variety of phenomena. Parity violation, they can be, the electronic structure is sensitive to presence of particle EDMs or electronic or hadronic EDMs. We can use atoms and molecules to look for variation of constants, try to detect dark matter and so on. And I think in Mainz there are plenty of such experiments being done. Yes, so furthermore, nice thing about atoms and molecules is that the electronic structure acts as a sort of amplifier and enhances these really tiny effects, which leads to higher sensitivity of such experiments. And then on the practical side, these experiments are small scale, so they're easy to initiate, easy to organize. They don't require large facilities or huge collaborations. And they're also relatively cheap, especially if you compare them to accelerator studies. So there's a lot of activity in this field. There's many experiments done all over the world. And there is actually a very nice review from a couple of years ago, which gives an excellent overview of the field. If you're interested, I would recommend looking into this. Right. So the next question to answer is, okay, how does computational chemistry or atomic and molecular theory come into this story? Because so we have particle theorists who develop new models or predict new phenomena. You have experimental scientists trying to detect it. And also theory in terms of atomic and molecular theory can be very useful here because of the nature of these experiments. So we're trying to measure very small effects, which means that for success of the measurements, we need to be able to, we need to choose systems which are sensitive, which are very well suited for such measurements. Of course, on the experimental sides, we need very sensitive equipment. We need very clever measurement schemes and so on. And an important factor in the success of such experiments is also strong and reliable theoretical support. And from our side, we can what we can do from our side is, first of all, using the computational methods, using our understanding of the electronic structure of the wave function, we can get some insights or understanding of the effect of this phenomena on molecular properties, molecular atomic properties on electronic structure. Using this understanding, we can propose promising candidates for measurements. So this would be systems which experience high sensitivity to whatever we're looking for, but also you could have some practical experimental considerations. For example, we need to know that the system is stable, or if depending on the desired experimental setup, we need to see whether it's laser coolable or we can trap it or whatever it is. So that's something that we can explore theoretically. If we do settle on the system, then also selection of optimal measurement scheme is often requires input from theory. One often needs parameters, atomic molecular parameters for experiments, which are not known a priori and which can be calculated. And finally, also, these experiments cannot be interpreted without input from theory, because what is measured is usually energy, so energy shifts, energy differences, from which we can extract the fundamental parameters that we're interested in using coupling constants that come from atomic or molecular structure calculations. And these coupling constants cannot be measured. So we need this theoretical analysis to interpret the results. All right, so we can, so there's many points. We can be useful in all, or theory can be very useful in all stages of experiment, from the initial vision to final interpretation. But that means, to be useful, that means that we need to be able to provide reliable predictions, which are based on high accuracy calculations. This means that we prefer using ab initio methods to have strongest predictive power. And we also need to be able to assign uncertainties on our results to make them directly comparable to experiment. And all these requirements mean that our choice of computational methods becomes very important. So we need to have a method which is exactly suited for this kind of studies. Okay, so here I come to the next part of my talk, to the computational methods that we use. And in order to visualize this discussion, I use this slide here, which represents the parameter space of various computational methods. So any ab initio computational approach can be found somewhere in this space. The three axes represent the three parameters which affect the quality of any calculation. So you have, and as we go along the axis, then we improve the quality of the treatment of this parameter, and unfortunately at the same time increase the computational cost, but that's life. So first parameter is treatment of relativity. We have non-relativistic Hartree-Fock here at the origin. So here we have the non-relativistic domain, and we go up on the axis until we reach relativistic methods and also some bright and QED corrections. Right, the second axis is treatment of electron correlation or instantaneous interaction between the electrons beyond the Hartree-Fock model. So at the origin, we have Hartree-Fock, which neglects correlation altogether. Here we have full CI, which is a complete way of including electron correlation, but is only suitable for atoms with just a few electrons. And we have the spectrum of the methods in between. And this is the choice of basis set, or basis set is a set of functions that we use to model a wave function. And again, basis sets can be small or very large. So the question is, where do we find ourselves in this computational landscape? And this depends on what we're trying to achieve. So it depends on the type of system that we want to look at and on the accuracy that we want to achieve. For example, most of computational organic chemistry will happen here in non-relativistic domain because these are large molecules composed of light elements. So there is no point wasting effort on using relativistic methods. In our case, we have the opposite situation. So what we want to calculate is these various coupling parameters that describe the effect of parity or time reversal symmetry violating phenomena on electronic structure. These effects are relativistic in nature, which means that we need to use relativistic methods. Also, if we want to provide accurate parameters for various atoms and molecules for these experiments, we need relativistic methods, as usually we're dealing with heavy systems. We want to achieve high accuracy. That means that we need the best possible way of means of treating electron correlation and large basis sets. And we also want to be able to evaluate uncertainties, which requires us to use robust methods, methods which are transparent and which can be improved systematically, so not black box approaches. All right, with this shopping list, we come back to the plot that we saw before, and I have marked where we are on this plot approximately. So we're using the relativistic Hamiltonian. We need to include relativity implicitly. We also use a couple cluster approach, which is the most accurate way of method for treatment of correlation if we're looking at many electron heavy systems. And we also use very large basis sets to take full advantage of the sophisticated computational methods that we're using. Right, so this method is called relativistic couple cluster. It's based on the 4-component Dirac Hamiltonian. It's very accurate, very powerful. It has nice properties like being size extensive and size consistent, which means that we treat molecules. So it's very good for treating molecules, for treating dissociation of molecules. It describes well properties of systems when they're together and when they're separate. Right, and we have two variants of this method. We have the single reference couple cluster, which works best for closed shell systems and systems with a very simple configuration, like a good example is ground state of barium fluoride molecule, single electron, doublet sigma ground state. And if we're interested in open shells, in excited states, in more complex configurations, then we'll use the multi-reference Fock space couple cluster. And if we talk about molecules, a good example is the triplet delta 1 state of thorium oxide, or any atomic spectrum which has many excitation energies. Depending on the problem and what we want to achieve, we will use one of these methods or even both of them together in complementary way. Yes, so I mentioned basis sets. Basis sets are sets of Gaussian functions that we use to represent the wave function of the system. Basis sets are specific for given atoms. You have also different sets which are optimized for calculation of different properties, different quality basis sets. The Gaussians would have different exponents because we need different exponents to describe the different areas in the atoms. So high exponent Gaussians are needed for the core region, diffuse Gaussians are needed for valence properties and bonding. And we use specially developed relativistic basis sets. We augment them and extend them to convergence of the results. Right, so what can we calculate? We can treat many different atomic properties, energies, spectra, but also hyperfine structure parameters, for example, and other properties. Molecular properties, geometries, spectroscopic parameters, Frank-Condon factors, basically whatever one needs to know about atoms or molecules. Then there's a whole zoo of properties which are specific for this kind of research. All these coupling constants for different types of phenomena. So coupling constants for ATM experiments, WD, WS. Coupling constants that one needs to interpret nuclear spin-dependent parity violation experiments, nuclear quadrupole moments, and so on. So different constants for different types of measurements. We can also calculate how the electronic structure will change with variation of constants, for example, fine structure constant. And we can, we have the possibility to extend our codes to include more parameters if needed. Our methods of choice are couple cluster, but we also can use Hartree-Fock or DFT methods. For example, when we want to investigate effect of correlation, or we would use DFT if we want to look at a very large system, and I'll give an example towards the end. And then we also usually perform systematic investigations of effect of computational parameters on our results, and in order to evaluate uncertainties. And this uncertainty evaluation is not a very straightforward topic in computational chemistry, at least. There is no clear prescription on how it's done. We use sort of an ad hoc approach, which is justified by the nature of couple cluster method, where we have a very clear idea of the effects that we include in our calculation, and we know what we're missing. We can really break it down to these three axes, and we can know what we're missing on each of these three axes. We can try to estimate these missing effects and use them to set very conservative uncertainties on our predictions. And again, you'll see an example of this a bit further on. Right, so this is a slide that kind of summarizes what I've said already. I think all these things, I mentioned. Generally, the accuracy that we expect is on the orders of tens of millielectron volts for energy properties. So we can do better if needed. So we can improve these results, and similar relative accuracy for most of the properties. There are also some drawbacks of this approach. So first of all, it's computationally expensive. Then the Fock-space couple cluster, the method we use for spectra, is limited for the moment to systems with up to 2 valence electrons or holes. And at the moment, we do not have implementations for all the properties we want to calculate. And while the first limitation is inherent to the method, so you want high quality, you pay for this basically in terms of computational time. The other two limitations are more technical in nature, and there's actually work in my group going on to extend the methods and to overcome these problems. All right, I'm reaching applications. Right, I don't know if there may be some questions so far, I can answer them, or should we?
Yeah, I would love to ask a question if I may.
Yeah.
Hi, Nastya.
Hello.
It seems to me that what you are describing is sort of an evolution of traditional methods of how atomic and molecular calculations are done. And what I'm wondering is we're witnessing some sort of new approaches. For example, machine learning, which is something that's maybe not so algorithmical, but some new concepts are there. And of course, people are now reaching the practical realization of quantum devices. So my question is, can modern machine learning and in the near future quantum computation make a difference here in this field?
I think quantum computation, yes. I'm a bit skeptical about machine learning because these are really methods that you need to, this is really not black box approaches. In the sense, you really need a human to think about what's happening. So I know that machine learning is used a lot in kind of proper computational chemistry already. So protein studies and so on, where the methods are, more, well, not straightforward, but more of black box methods where there's not so many decisions to be made. So I myself don't really see a way of reaching this state with our approaches yet. But quantum computing, sure. I mean, hopefully it will allow us to run much bigger calculations much faster. So
how many qubits do you need to make a difference in practice for what you're doing?
What do you mean in terms of?
Well, you know, in this business, the main parameter is how many qubits are in your quantum computer, right?
Well, that's not. One of my collaborators, Ephraim Eliav, is actually looking into this now, but I'm not really. I don't really know this.
Thank you.
Yeah. Yes. Are there more questions?
There is a question from Ferdinand in the chat.
Yeah.
Well, I just want to add that, of course, chemical calculations are already executed on quantum computers, of course, in small systems and toy models and so on. But this is a true used case. But so far, this is just a Wigner-Jordan transformation to get from the Fermat problem into a qubit problem, to implement this then on a qubit machine. But so far, as far as I know, there are not the slightest relativistic things included. So this would be really interesting to see how far one can go there. That is really an interesting aspect, I think.
Yeah, I think there's also the program that we use is called Dirac, and it's a computational chemistry software. And I know there are plans to also kind of extend it into quantum computing, but which would be very nice, but I don't really know details.
Mm-hmm.
Yeah.
Another question by Alexei.
Yes, if I can ask a question. Hi. So I would like to ask now, you're mentioning the couple cluster method, right? And okay, I just heard about it before. It's really new for me, but I heard also from a tutorial by, I think his name is Julian. I forgot the last name. I'm sorry, the person from Australia. About the CI, and I also read from I think Safranova, the CI and BPT, and also including packages available that are supposed to be useful. Could you compare those? I mean, sort of why? Because those packages are, well, let's say, marketed in the sense that they can be used well by non-theorists for theoretical calculations. I mean, given some programming experience, of course. Yeah. Could you comment on that, please? Thank you.
Well, I think so. These are excellent packages. I mean, I know both these groups, of course, and the work they do. I think what you need is not so much programming experience, but some kind of experience in carrying out calculations. So this sort of intuition, which I guess one gets from doing this kind of work. But yeah, so again, with this, you can, in principle, so when you ask me to comment, what?
Yeah, so what I wanted to ask more is could you comment on let's say the differences in approach, and I guess maybe in the usefulness of the different methods of, let's say, the couple cluster method as opposed to the CI and BPT methods, because they both exist and they both are supposed to be useful, but I guess in different circumstances. So that's what I mean more.
Yes. So I would compare the Fock-space couple cluster, the method I mentioned, which is suitable for energy calculations for excited states, to CI and BPT because it's similar use cases. So CI and BPT has a wider application possibility. I mentioned that we're limited for the moment to 2 valence particles, valence holes. With CI plus BPT, you can do more than that. So yeah, in this case, it's wider. It's more straightforward to achieve high accuracy with coupled cluster. It's basically it's cheaper to reach. So reaching the same accuracy is cheaper in coupled cluster, which means that with the same we can go further with computational resources. Yeah, but we can also we can certainly achieve comparable accuracy as well. So in a way, it's also a matter of preference.
Okay. Thank you.
All right, so I'll continue to show some examples of research we carry out with using these methods. And I have, I selected two examples. One is has to do with search for electric electron dipole moment in barium fluoride molecules. And another example is new work, search for parity violation in chiral molecules. All right. So the first topic is the experiment theory corporation called the NLEDM, the aim of which is to measure the electron electric dipole moment using cold and slow barium fluoride molecules. This is a collaboration of scientists from University of Groningen and Free University of Amsterdam. We have 7 researchers involved, 2 of them theorists. My group is in charge of atomic and molecular theory, and Rob Timmermans on the particle physics side. Here's a picture of people who participate in this work, and this picture is a couple of years old. We now have many more master students involved as well. So this is a very lively, very active collaboration. Yes, so the aim of this work is to try to measure the electric dipole moment of the electron. So normally we say electron should not have dipole moment, it's a point particle. And such dipole moment would violate both time reversal symmetry and parity symmetry, as is illustrated here. So if we apply, it would be aligned with the spin. If we apply parity transformation, we get one picture. If I apply time reversal transformation, we get another picture. So we break the symmetry. And in fact, the standard model predicts, standard model allows such breaking of symmetry and allows the existence of electric dipole moment of the electron, but predicts it to be extremely small, on the order of 10 to the power of minus 38 e centimeters. So this is too small to be measured with the modern methods. The various extensions to the standard model predict much larger values, much larger, I mean many orders of magnitude larger, which bring this effect into a measurable regime. And the measurement of, confirmation of existence of electron electric dipole moment would provide an unambiguous signal of new physics and will give us a lot of information about these new theories. So that's the attraction of this measurement. How does one measure the EDM? So taking a free electron and trying to measure the dipole moment using the external electric field will not go well. The effect would still be too small, and also the electron would leave, basically. It's a charged particle. So we need to use, we need to have something to keep the electron in place and to amplify the effects. And for that, we use a molecule. So molecular, So instead of measuring the EDM of a single electron, we'll perform a measurement in a molecule where electronic structure will amplify the effects of this electron electric dipole moment. So what we measure in practice is not anymore the EDM of the electron, but rather the parity time violating EDM of the molecule induced by this electronic EDM. All right. Right. So these measurements in molecules are being carried out for a while now. There is a number of main experiments on ytterbium fluoride, thorium oxide, hafnium fluoride plus, and barium fluoride, which is done in Groningen. We here have the order of magnitude of electron ETM. On the bottom of the screen, we have the prediction of the standard model, this 10 to the minus 38. Here, this dashed area is predictions of various standard model extensions, and I think they extend even further down as well. A shaded area is size which is already ruled out by experiments, so various upper limits which were already set. And here there's the line which shows the projected projected sensitivity of this experiment on barium fluoride. The reason that barium fluoride was selected was mainly because of practical advantages. This molecule has a simple electronic structure, so it makes it easy to manipulate. It should be easy for laser cooling and for stack deceleration. Barium fluoride, as any molecule, experiences enhancement of the effect. So it enhances the interaction between the dipole moment of the electron and the external electric field in the experiment. But this enhancement is not larger than in other systems of comparable atomic number. So in this sense, it's not special. What is done in practice is that what is measured is tiny energy difference, tiny shifts in energy of the hyperfine states of barium fluoride for different configurations of electric and magnetic field. For the configuration where they are parallel and where they're anti-parallel, this will, this energy shift is shown here, and it will be proportional to the magnitude of dE, of the electric dipole moment, times this effective electric field, which is an enhancement effect of the molecule. The sensitivity of such experiment is shown here. And we have here on the bottom WD, which is another way of writing E effective. So there is a relation between these two parameters. So this is statistical sensitivity. It's determined by this expression. Of course, once we selected the molecule, we cannot change WD anymore. But we also have here the interaction time and the number of particles, which we can try to increase to achieve high sensitivity. And this explains the setup of the experiment. The molecules are created in the cryogenic source. They are slowed down by a Stark decelerator. They are laser cooled here to kind of make the beam to lower the transverse velocity, so to keep the molecules in the beam. And basically, we hope to achieve a very large number of slow molecules in the interaction zone. And here we have the detection. We published a paper describing the setup and the experimental proposal. And I will focus now on calculations that we perform from our side for which I needed to plan and carry out this experiment. And I focus on the two parts of this. So we have laser cooling, which is here. So we need to provide recommendations on the laser cooling scheme and the optical detection. So here we need also to provide parameters which are needed for interpretation of the measurements. All right, so I'll start with laser cooling. So again, the idea is to use laser cooling to slow so we already slowed the motion of the molecule in the beam direction by the Stark decelerator. And now we want to slow the transverse motion to prevent them to kind of from dissipating. So we want to use laser cooling for that. In order to have efficient laser cooling, we want, there's a number of conditions, but we want to have short lifetimes of the excited state for efficiency so that we decay fast and we can absorb many photons. And we want to have a closed cycle. So we try to not have some kind of intermediate levels where long-lived levels where the molecules can get stuck and be out of the cooling cycle. And in the molecules, we have an additional complication because of vibrational structure. So every electronic state supports a number of vibrational levels. And here also, basically what we want to achieve is to have our cooling transition to go from the ground vibrational state of the, of the ground vibrational level of the ground electronic state to the lowest vibrational level of the excited state, and to decay, to fall back into the same level. So again, achieving this closed cycling. We do not want to have situations like this where we go to some high vibrational state and decay to various different vibrational states in the ground state, because then we lose the molecules. And we can predict whether this we can achieve this state by using a measure called the Frank-Condon factors. These are factors we can calculate from overlap of the vibrational functions over different states. Yeah, we can also plot them in this way, where you have the vibrational number of the excited state, vibrational number of the ground state. And the dark color stands for probability of transition, basically, between the different states. So if we have this diagonal structure, that means that you're likely to have transition to the same vibrational level, which is what we want. All right, so yeah, so we wanted, before building the cooling setup, we needed to explore whether, first of all, whether barium fluoride can be laser cooled in this kind of scheme, and what transitions is optimal for laser cooling. For that, we needed to know a lot of spectroscopic parameters. We needed the potential energy curves, spectroscopic constants, Frank-Condon factors, transition dipole moments, and so on. We performed these calculations using a relativistic Fox-based coupled cluster for the lowest 6 states in barium fluoride, shown here, and also corresponding states in the lighter homologue, strontium fluoride and calcium fluoride. These molecules are expected to have similar electronic structure, and they were already laser cooled in the past. So this is a good test case. And we had to decide between 2 possible cooling schemes. One which is shown here, which was used for calcium fluoride in the past successfully, so sigma to sigma transition. And the second, sigma to pi transition, which was also used both in calcium and strontium fluoride. Because both these transitions are allowed, what will determine which one is better is the Frank-Condon factors, which I talked about already. So we calculate these Frank-Condon factors to see which would be a more promising choice of cooling scheme. We first look at the first possibility. Indeed, in calcium fluoride, this is extremely diagonal, which was why it worked so well. But we see that for barium fluoride, the picture is entirely different, and we would not get this closed cycle for this transition. So it's immediately clear that this is not the way to go. On the other hand, if we look at the second possibility, so yeah, this is not as good as calcium fluoride, but still we have, for the lower states, we have this diagonal Frank-Condon factors. So we expect that in this case, this would work quite well. So based on this transition, we we determined the laser cooling scheme. Because they are not ideally diagonal, we still lose some molecules to higher vibrational states, and we can use extra repump lasers to return them to the cooling cycle. And we find that if we have 2 repump lasers, we can actually scatter around 2000 photons, which should be sufficient for the transverse laser cooling that we have in mind. And so this is the cooling scheme that will be used in the experiment. This work was done by my PhD student, Yonlian Hao, who is now working in China. And it was published couple of years ago. So,
excuse me.
yeah.
It's 2000 photons. What happens then? I mean, do you lose basically the molecule from the cooling cycle, or do you?
Yeah.
Or what?
So that's okay. Based on the branching ratios.
No.
Nastya, since you've been already interrupted, I may ask you also, what are the rotational quantum numbers?
In the experiment?
Mm-hmm.
I think they should appear in the slide. I think it's the lowest ones. So
okay. Yeah.
It's MF 0, 1, and -1. So it's rotational quantum numbers.
Very low. Okay.
Very low. Yeah.
The other question I have is, when you consider laser cooling schemes, have you looked at the relatively recent developments with stimulated cooling, rapid adiabatic passage cooling, and things like that, which may mitigate the problem with leakage into the states that need to be repumped?
No, I haven't, but I will now. That's
good.
Yeah, thank you.
Yeah, yes.
Right, so this was for laser cooling. Okay, but also at some point the measurement will be performed, and we're hoping, well, for at least to get a new upper limit on the electron EDM, to at least get a new upper limit, or perhaps even have a measurement of the effect. And at that stage, we would need to interpret the experiment. And I talked about this parity and time violating electric dipole moment, which is molecular dipole moment, which is induced by the electron EDM. But in practice, this is not the only thing that might contribute to this molecular EDM. We also have this scalar pseudoscalar electron nucleon interaction, designated by kappa S, which could contribute in a similar way. So the total effect is shown in this expression. Here D is the electron EDM, kappa S is the interaction strength of this interaction, and WD and WS are parameters, electronic structure parameters, which are specific to the molecule, which come from molecular theory. So eventually what is measured, this energy difference, can be interpreted in terms of this expression. And you can immediately see, first of all, that we have here two unknowns in one expression, which means that we cannot, actually from a single measurement, we cannot separate them. So what we can get is this kind of exclusion plots rather than a single value. And one would need more than one measurement on very different systems to get an ambiguous value for DE or kappa S. So that's something to comment. But even for such an exclusion plot, we still need the accurate values of these coupling parameters, WD and WS, which come from theory, and which was our job to calculate. Here I have the explicit expressions for these parameters. And we use the relativistic couple cluster, singular reference couple cluster in this case, to calculate them. The method was already selected, but there are still a number of computational parameters that we can improve to, or we can vary to improve our calculation and extend our results to convergence, like quality of the basis set, which I mentioned, or how many orbitals we correlate. And we also performed the computational study to estimate uncertainties. As I said, we kind of tried to figure out what we're still missing on each of the three axes. And basically the way of making these estimates is to take the a parameter corresponding to the best possible calculation we can perform and compare it to what we get with the second best parameter and take it as a hand-waving estimate for higher order effects. Here we have the breakdown of these effects in various parameters that we can vary. Here I have collected them together according to the three axes. We can classify these effects in terms of relativity, electron correlation, and the basis set effects. And we end up with the uncertainty of less than 2%, which is mostly due to missing relativistic effects. So higher order bright and QED corrections. Here we have the final recommended values for both constants, including the uncertainties. We can compare them to previous calculations. This system was actually used many times as a test system for different methods. So we have a large number of results to compare to in different, very varying quality. Everything to the right of the green line is a couple cluster methods. So in principle, these results should agree well with each other, which they do, which is good news. Because again, we are predicting parameters where no experiment is available or even possible. The present prediction gives the tightest error bars so far, which is nice. Right, this work was done by my PhD student, Pi Hase, and she's now completing the work on the manuscript. And okay, so we look at these results, and this is, of course, quite nice. We have the numbers, we have the uncertainties, but we have a problem here because, well, these parameters cannot be measured. So there is not really a simple way to prove my claims, my claimed predictions and my claimed uncertainty. And this, so we still would like to have some way to also connect this, take it out of the realm of computational study and connect these numbers somehow to reality. And we have a way of doing that by using, so for a property where no experiment is available, we can use the same computational method, the same computational scheme on a proxy property to use as a sanity check. So we take a similar property and perform the same calculation, evaluate uncertainties in the same way. And that property should have experimental values available, which we can compare to what we get and see whether results make sense. In this case, we selected as proxy the magnetic hyperfine structure constants in barium fluoride molecule. So this is a good choice because first of all, it's the same molecule, same electronic state. And also, like the parity violating parameters, these constants are expected to be sensitive to how well we describe the nuclear region. So in a sense, they would have similar computational requirements. We then calculate this hyperfine structure constants for barium and barium fluoride, the parallel and perpendicular ones, and we compare them to measurements. There is accurate experiment available. And we see that, we also have estimation of uncertainties. And we see that indeed our results are really in very good agreement with experiment. It seems like our uncertainty are over conservative. So we seem to overestimate the uncertainties. So we're still looking for ways of setting tighter error bars on such predictions. But in principle, so this kind of comparison confirms reliability of our predictions for WS and WD, where we cannot make this comparison of this sort. So this is quite nice. Right, and this was published also very recently this year. I'm going to switch to a new topic, so maybe if there are questions on this one, that could be a good time.
Are there questions?
If not, I can also continue and have the questions at the end.
Yes.
All right. So now I'm going to talk about something completely different, as the slide tells you. change topic. And yeah, I will tell a bit about some very new work that we did and which I'm quite excited about. This is a new kind of topic for me. It has to do with search for parity violation in chiral molecules, a topic that many of you are familiar with. So chiral molecules come in two enantiomers, which are mirror images of each other and which cannot be superimposed on each other, as is presented in this picture. And yeah, so the question we're asking is there a difference in the properties of right and left-handed enantiomers due to parity violation? So that's a question we're trying to answer. And we know that parity violation is happens in weak interactions, and it's been experimentally detected in nuclear decay and an atomic physics experiment on cesium. So this is an established phenomenon. And in principle, in chiral molecules, we should also see this effect because of the interaction between the electron and the nuclei, the weak neutral current interactions. And this effect should lead to tiny energy differences between the two enantiomers. And this is a very attractive proposition because if such a difference exists, it could help us explain the origins of biohomochirality. Yes, so biohomochirality, this, so in principle in the lab, we have equal chances to produce left or right-handed amino acids or sugars. But in all living organisms, we always have left-handed amino acids and right-handed sugars on all the living things on Earth. And in a sense, it's okay, and that's how it should be to sustain life, because of course, you want uniformity, so you want these molecules to fit to each other. So once a preference is established, once we have left-handed amino acids, then we will always have right-handed sugars. And we can see that this preference was appeared very long ago if all organisms are like that. But the question is, how is it a random decision in a sense to this left-right? Could it have been the other way around with same probability? Or is there some kind of energetic reason for that? And yeah, so parity violation could cause a tiny energy difference between these enantiomers, which could cause a small excess of one over the other, which amplified over the time could lead to this predominance. So this is one possible explanation of biohomochirality. This is a very debated topic, but in general, before, in order to study this possibility, of course, first of all, one needs to detect parity violation in chiral molecules, and one needs to measure the order of magnitude of this effect. So in order to have anything sensible to say about this, so far, no, it has not been detected, and there is experiments that search for this effect. Because parity violation is expected to affect all molecular properties, we can look for it in different types of transitions, in electronic structure, or electronic transitions in NMR spectroscopy, which is done in Mainz, of course, and also in vibrational spectroscopy, which is what I'm interested in here. Right. So in vibrational spectroscopy, rather than looking at the absolute difference in rather than looking at the difference in absolute energies between enantiomers, we look for small differences in the vibrational transitions of the two enantiomers. Yeah, so pretty straightforward. Such measurements were already performed in the past at LPL in Paris on the CF stretch vibration in fluorochlorobromomethane, a molecule that is shown here on this figure. Here's some figures for the experimental setup. In this experiment, there was no detection of parity violation, but it set an upper limit of about 10 to the minus 13 on the relative effect. So delta nu PV is the difference in the transition frequencies of the two enantiomers, with the nu is the transition frequency. So an upper limit was set, and after the fact, theoretical studies showed that actually the predicted effect in this molecule is a few orders of magnitude smaller. I think 3-4 orders of magnitude smaller than this. So it could not be measured. Also, the selected stretching vibration was unfortunate. I think there the effect was even smaller than other ones. But in general, because the molecule is composed of light atoms, the effects are very small, which means that we need a better molecule, a better candidate. And such a better candidate, there's a whole shopping list of requirements that it should fulfill. Of course, it should be stable, commercially available. We should be able to separate racemic mixture into pure enantiomers for this kind of measurement. We should be able to bring it into gas phase, probably by laser ablation without it falling apart. We want it to contain heavy elements because the absolute parity violating energy is predicted to scale as z to the power of 5. And we want to have it to have strong vibrational transitions in the range of the lasers. Yeah, so there's a number of lasers in that lab and LPL, but this is the range more or less. Also, in the meanwhile, the experiment has been upgraded and updated. So now it's also more sensitive. It can detect relative effects on the order of 10 to the minus 15. And so this is the order of magnitude of the effect that we're looking for. All right. And one such candidate molecule was selected. It's called ruthenium ACAC3. So we have the metal in the middle and some ligands on the sides. This is how this molecule looks. And if you're wondering how it can be chiral, because it's very different from the previous molecule I've shown you, it's less intuitive. Well, it has what's called propeller-like chirality. If you think about a propeller, then you realize that they're chiral. I mean, if you have some kind of bend here. So yeah, it comes into enantiomers. And this molecule ticks all the boxes in the shopping list. But what we do not know a priori is how large the effect is, how large the parity violation effects are expected to be. Yeah, so we want to know whether they're large enough to be detectable in this experiment, where it makes sense to use this molecule in these measurements. For that, we performed so to find this out, we performed the calculations of this effect in this molecule. In this case, we used the relativistic DFT method, density functional theory, because we have a many electron system, and we also want to investigate a lot of vibrational modes. So in this case, and on the other hand, we want to know the order of magnitude of the effect rather than the exact value. So in this case, we compromise on quality for efficiency, and we perform calculations on many vibrational modes. We could identify some modes with either very large shifts in vibrational frequency on the order of a few hundreds of millihertz, or vibrations which are in the range of the lasers with a slightly smaller parity violating shift, but still large enough to cross this 10 to the minus 15 line. So indeed, we identified a number of transitions, a number of vibrational modes where this kind of measurement looks promising. And so this kind of study can also help in selecting the vibrational mode to focus on. Right. At the same time, we also looked beyond this particular system. We looked at its heavier homologue, Osmium Iii, so where ruthenium is replaced by osmium, its heavier homologue. Yeah, so for the same vibrational modes, we have even larger effects in the osmium-containing compound of the order of 10 to the minus 13 because of this enhancement with the atomic number. Actually, the scaling is better than Z to the 5 predicted for total parity relating energies, which means that we should probably investigate the scaling law in vibrational transitions, what determines that. Yeah, so this looks like an even more promising system. On the other hand, we do not know whether it ticks all the practical boxes. So there are still some practical challenges to be solved if one wants to use it. And yeah, so this work was done by my bachelor student, Mariette Fichter. She's now in ETH Zurich, and we're doing this in collaboration with Benoit Darquet from LLP and Jean Crassons from Rennes. And also, yeah, my PhD student, Pihaze, and Lukasz Paszteka, who we work together with on this kind of projects. And this also kind of, so this looks very promising. We also, it opens a wide kind of range of studies, looking at different types of compounds, different metals, different ligands, and so on. So this is quite interesting type of molecule to look at. Right, so these are preliminary numbers. We're now working on the paper. And yeah, I reached the end of my talk. So I don't have so much to say in terms of conclusions. I have shown the methods that we use, which are tailor-made for this kind of calculations. We can use these methods to treat very different types of problems, achieve different types of different levels of accuracy. This is quite versatile. We can also provide uncertainty estimates, which is nice when working with experimental groups. And yeah, so these uncertainty estimates make us much more popular with our experimental colleagues. And these collaborations are very interesting, of course. And on the general note, I think there is so many of these experiments which are more and more sensitive. And I think we're going to see a lot of very interesting discoveries in the near future. So it's also a very nice time to be working in this field, I think. Right. I'd like to acknowledge my colleagues on the theory side, Victor Flambaum, Ephraim Eliav, Miro Elias, Peter Schwertfeger, and Lukasz Paszteka. And yeah, I think I'm done here. And thank you for your attention.
Thanks for the nice talk. This is probably the nicest picture of Victor Flambaum that I've ever seen.
Great. Thank you very much, Nastya. I have one question here in the chat room, but also please, I ask James Ills to ask the question himself.
Just a second, I kind of lost the Zoom screen on my laptop.
Okay.
Yeah, found it.
So, yeah, please.
So my question was, like, clearly going to these much heavier compounds with transition metals is hugely advantageous because you get like a huge increase in Z, but the molecules are lower symmetry than like the point chiral molecules you were looking at. Do you have any sense of how that affects the size of the expected shifts?
So you mean
I mean, there are more symmetry operations on the axially chiral molecule. Like the symmetry group is D3, I think. Whereas for a point chiral molecule, it is just there's just one symmetry operation, is the identity. Do you have any sense of how that affects the size of the effects that you're looking for?
For the propeller that Anastasia has shown, I think it has many symmetries.
Yeah. No.
Yes. Yeah.
Yeah, I think that's D3 indeed. No, that's a good question. I'm thinking because we're looking also at other compounds which have also which are C1 symmetry. And there the effect is larger for a similar metal, for a similar atomic number.
Okay.
Very hand-wavingly, I think perhaps reducing symmetry makes the effect bigger, but I never thought of looking at this in this way.
Okay.
So this osmium Iii, is it? Do you think it may be available, maybe stable, or what do you know about it?
So it's been synthesized. I mean, it's not our invention, and it is stable. I think it's not commercially available, but it can be synthesized, and as far
not rhenium, but not rutetium, sorry, but osmium.
Also osmium, yeah.
And can you potentially calculate the parity violation in NMR for this thing? What osmium, for example, 187 has spin 1/2. So it's potentially a good nucleus for.
Yeah, potentially yes. So it's a very different computational setup, but yeah, that's not. There is no reason of why not. Yes, certainly.
Ferdinand?
Yeah, I would like to ask also about the ideal molecule. Wouldn't that be something like a fullerene and inside only one heavy ion? Because then the symmetry is completely broken and the heavy ion gives you enough relativistic effects. So that would be my guess, so to say, extrapolating from your planar structures to even more symmetric ones.
Well, we're looking, so we don't have results yet, but we're starting to look at this kind of, well, not really fullerenes, but fullerene-like systems, which are built of gold metals, for example, gold atoms. So heavy, also heavy cage.
Yeah.
So yeah, that sounds cool. We haven't got any results yet, but yes, that's.
Thank you.
Any further questions? Yeah, it seems not to be the case. And I would like to thank Nastia again for this nice talk.
Well, yeah, thank you very much for having me here.
Yeah, thank you. Yeah, with this, I think we can close now the session. That's it for today. Thank you very much.
Thank you. I hope to see everyone in person before too long.
Yeah.
Nice talk.
Thank you.